We have all seen operators chase the furnace, reacting to symptom rather than root causes. Today we are establishing a yardstick approach, a set of universal predictive formula that turns raw data into operational foresight. So by end of this session, you will able to quantify exactly how raw material changes impact your raft. It also helps in calculating productivity gains from the reductant efficiency, and it navigate the complex butterfly effect of pulverized coal injection. On the screen you see a master schematic of the furnace and its peripherals, glowing with the thermal gradient from the hearth to the top gas equipment. This is not just an illustration, it's a physical manifestation of the thermodynamics we are about to quantify. So mastering this relation is your first step towards the process control. To apply this yardstick, we must first understand the five pillars that define every single prediction we make on the floor. And our next slide exactly addresses these five pillars, and it's supposed to be a very important slide. So look at this central HUD graphic. It is our operational dashboard. We have categorized the furnace into five pillars, that is thermal control, the productivity, the aerodynamics, chemistry, and vessel integrity. So notice the circular dial. It shows the real-time status indicator like a 95% productivity rate and a 5.2 bar almost pressure drop. So while every vessel on this planet is unique in its geometry, these five pillars are connected by the universal relation. The so what here is vital. You cannot adjust your chemistry without impacting your aerodynamics. For instance, a hazard in the chem sector like high sulfur. So often it requires a thermal adjustment in the thermal sector that could stress your vessel integrity. As mentor, we teach that mastery is about the balance between these five segments. If one red lines the entire campaign is at the risk. So we start our deep dive with the primary thermal lever, the raft. The most immediate way to manipulate this pillar is through the blast parameter and their impact on flame temperature. Now the raft and top gas matrix, which is the title of our slide, observe this balance scale. On the left we have the flame representing raft, on the right the cloud representing the top gas temperature. This matrix provide the linear yardstick for the process control. So look at the top row, adding 100 degree to the blast temperature, spike your flame or raft, where you can say raceway flame adiabatic temperature by 52.8 degrees, while cooling the top gas, the so what option, and the factor is here 0.6% gain in gas utilization or ATSGO. Conversely, adding 10 kilogram of coal act as a thermal sink, dropping raft by 26.6 degrees. This is a coupled reaction. You cannot change your fuel mix without rebalancing your high heat. So if you don't account for this offset, you will lose your thermal reserve zone, leading to inconsistent hot metal chemistry. We use this precise mathematical relation to ensure that every input shift is compensated for by a corresponding blast adjustment. So while thermal balance keeps the furnace hot, our ultimate goal is maximizing the productivity engine. And so coming to our next slide, we on the productivity engine. So as you can see on the left, the slack burden gauge shows a penalty of 0.0 0.05 ton per cubic meter for every 10 kilogram increase in slag rate. In the center, the reductant efficiency gauge highlights the gold standard. Every 3.5 kilogram drop in total reductant rate yield a 1% boost in total output. Finally, the lump penalty gauge on the right reminds us that gas restrictive lump ore carries a 50 kilogram coke penalty. The so what is clear. Efficiency drives out. If you can optimize your burden to lower reductant, you are not just saving on fuel cost. You are physically opening up volume for more iron production. This is the productivity engine in action. However, to achieve this output gain, we must first overcome the physical blockade of the burden itself and the aerodynamics of gas flow. This productivity is physically limited by the permeability of the material we charge into the top. So we need to talk about the material blockade. So look at the comparison on the left. Sinter at the 14 millimeter creates high flow resistance while 40 millimeter coke has 4 to 5 times lower resistance. So notice how the sinter curve spikes sharply. Over 80% of your total gas flow resistance comes from that burden, that is that ferrous burden. Now look at the Bernoulli's funnel on the right. The math is unforgiving. To punch twice the gas volume through the furnace, your blower pressure must quadruple. So the operational impact is hard selling on the productivity. If your burden quality degrade and the fines increase, you will hit a pressure move limit that prevent you from blowing the wind required for your production target. So you must manage the material blockade to keep the Bernoulli's funnel open. These must then exit through the tuyeres. The velocity at which that gas enters the furnace is dictated by the regional strategies and hardware benchmark. And coming over this slide, compares the operational strategies between Europe and Southeast Asia. In Europe and North America, we typically see lower velocity of 200 to 220 meter per second, relying on the burden distribution for valve flow. In Southeast Asia, they push 240 to 260 meter per second to minimize the central dead man. Below the table is the stability zone. We must maintain blast momentum between the 3000 and 9000 kilogram meter per second. If you drop below 3000 into that orange danger zone, your raceway becomes unstable, leading to catastrophic wear hit damage. The so what here is about equipment longevity. If your momentum is too low, the gas doesn't penetrate the furnace core, causing it to swell and burn through your copper hardware. This thermal instability often leads to the most dangerous heat drain of all. So when gas distribution fails, we risk an increase in direct reduction, which act as a massive thermal sink, which is just getting reflected in this slide. So now as you can see, the vortex is the direct reduction heat drain, as very clearly it's shown. FeO plus C is equal to Fe plus CO, and in process a lot of heat is getting observed. The equation is a thermal sink that requires 155 kilojoules per kilomole of iron. So this is the primary catalyst for the furnace chilling or freezing or coldness, we can say. So when direct reduction increases, is physically drain temperature from your thermal reserve zone, creating a self-accelerating cooling cycle. You can see the hearth chemistry baseline on the right. 94.5% iron and 0.4 to 0.6% silicon. So if your silicon levels start plummeting, It's a sign that this vortex is sucking the heat out of your heart. So you are losing fuel efficiency because your gas is not doing the job, doing the right work for you. So you are expensive and you have to invest with your expensive coke. So we measure the health of this gas solid exchange through the breadth of the furnace. To stop the heat drain, we must monitor the dry top gas utilization or ATCO. The breadth of the furnace is our next journey towards which this vertical meter already shown the breadth of the furnace. The green optimal health zone for the ATCO is between 45 and 50%. So when your dry top gas utilization is in this range, it means oxygen is being efficiently stripped from the body using less gas and less coke. The so what factor is direct. A higher ATCO translates immediate into a lower reductant rate and higher vessel efficiency. So if your meter drops below 40%, you are exhaling usable carbon monoxide that should have stayed in the furnace to reduce ore. This is often a sign of channeling or poor gas solid contact in the shaft. So as supervisor, this is your primary diagnostic for the chemical efficiency. It's if the breath is shallow, the furnace is struggling and you may be approaching the safety readiness of your input. The chemical efficiency is only possible if you respect the physical limit of the raw material entering the stack, which is supposed to be one of the most important deliverables of this slide. So coming to our next journey, that is towards the input safety ceiling. So we must respect the input safety ceiling shown on the cross section. In the upper stack, we limit zinc to 150 gram per ton of hot metal, which is very important boundary to prevent a damaging condensation cycle. At the refractory wall, alkali input must stay below 3 kilogram per ton of hot metal to prevent refractory attack. So most importantly, the cohesive zone grid requires a minimum metallurgical coke rate of 230 kilogram per ton of hot metal. The so what here is about the structural integrity. So if you drop below the coke limit, your cohesive zone collapse, blocking gas flow and liquid percolation. You cannot just keep swapping coke for the coke coke we can say in indefinitely. So there is a physical minimum required to keep the furnace breathing. So when you push this limit, you trigger a cascade of event we call the butterfly effect. Every decision to push the limit or change an injection rate ripple through the entire process. So we conclude with the butterfly effect, which follows the logic. The action to increase PCI rate trigger three simultaneously shift, three simultaneous shifts. So what are they? The first, it decreases the physical coke grid, risking your K factor limit. All operators should aid in memory this. Second, it is increases the total top temperature. Third, it lowers your draft. So to rebalance the vessel, these one action require a corresponding increase in oxygen enrichment to offset the thermal drop. So mastery over the blast furnace is not about optimizing one single variable. It's about balancing all above that we have discussed, which are interconnected and which give a cascade effect. So use the yardstick we have discussed today to predict these ripples before they becomes waves and before